Hello guys, so I welcome you in this lecture uh, which is going to be on binary heaps. Okay, so this is going to be the first lecture on binary heap. We are going to talk about some of the use cases, like use of this data structure. Okay, yeah, and then we'll talk about the implementation. Okay, how the elements are stored when we use the binary heap data structure. So let us quickly start with the lecture. So first thing that we're going to talk about is what is binary heap. Okay, so a binary heap is a data structure. Okay, data structure. Okay, in which the elements are stored on the basis of the priority. Okay, priority can be either either the elements are stored in the ascending order, or they're stored in the form of in the descending order. Okay, so let's just quickly start the introduction of binary heap. So binary heap is also called priority queue. Okay, priority queue. Okay, if you are already introduced with binary trees, so let me tell you that a binary heap is just similar to a complete binary tree. Okay, complete binary tree. Okay, now what is this complete binary tree? So let's just start with this. Okay, so yeah, complete binary tree. Okay, let's discuss about this complete binary tree. Okay, so what is a complete binary tree? We all know that a binary tree is a tree which has a root node. Okay, and each of the node can have at most two childs, right? So let's suppose this is a node. It can have two childs. Okay, it can have two childs, and then these two childs can also have two childs individually. Okay, so this node has two childs, then this node also has two childs. Okay, and then these four nodes can have two childs individually, like this is the substructure. Okay, so yeah, it goes on and on and on. Okay, so it has two nodes. Similarly, it has two as well. Okay, it has two as well, and similarly this also has two nodes. Okay, so yeah, it keeps going on. Okay, it keeps expanding by a factor of two. Okay, so this is a binary tree. Okay, this is a binary tree data structure. Okay, we call it a binary tree because we have two child nodes. Okay, binary tree. Now what is the complete binary tree? Okay, so let me tell you, a binary tree. Okay, a binary tree is called complete. A binary tree is called complete binary tree. Complete. Okay, if it is uh, completely filled, completely filled. Okay, except possibly the last level. The last level. uh, okay, except possibly the last level, which is partially filled from left to right. Okay, which is partially filled from left to right, from left to right. Okay, now what do I mean by this? So let's suppose we have a binary tree here. Okay, let's suppose we have a binary tree here. So let's say this is the root node, this is the root node. Okay, root node. Now this root node has two childs. Okay, okay, so two childs, and then let's say the third level is the last level, and this node do not have any child. Okay, so uh, this is the first level. Okay, first level. This is the second level, like this complete level is the second level. Okay, second. And let's say this was the third level. Okay, let's say, so third. Okay, so according to the definition, a binary tree is called complete if it is completely filled. Okay, either it is completely filled. So this binary tree is completely filled, like, you know, each nodes has two child nodes except the last nodes, which are also called leaf nodes. Okay, so all of these nodes which are at the bottommost level, they are called leaf nodes, and the topmost node is called root node. Okay, so this is also an example of complete binary tree. Okay, so according to definition, a binary tree is called complete if it is completely filled. Either it is completely filled or it is partially filled, but the order of partial filling is from left to right. So the left part is filled first, okay, and not right part. So this is what we call as a complete binary tree. Okay, complete binary tree. Okay, now let me tell you what is not called as a complete binary tree. Okay, so let's move it a little bit. Okay, so let's see. Okay, so we have this binary tree. Okay, it has two nodes. Then on the second level, and on the third level, it has one node here, and it has, let's say, one node here. Okay, so let's see. Okay, so this is the root node. Okay, so this is the root node. Then according to level, let's say, so this is the first level, this is going to be the second level, right, and this is the last level. Okay, which is third, obviously. Third is the last level here. So we can see that according to the definition, a binary tree is called complete if it is completely filled except the last level, which is filled from left to right. So we don't have a node here on the left side, and we don't have a node here as well. So it is not filled in the order from left to right, right? It has one node here and one node at the rightmost position. Okay, so this won't be called as complete binary tree. Okay, so this is not a complete binary tree. Okay, not a complete uh, binary tree, not a complete binary tree. Okay, now let's see. Okay, so now we know what is a complete binary tree. We also must know that the elements in a binary heap. Okay, so the elements in a binary heap are stored in the form of an array. Okay, they're stored in an array only. Okay, so let me tell you how the implementation takes place. So yeah, so implementation of a main heap. Okay, main heap, not main heap actually. So I haven't told you about main heap and max heap, right? So implementation of a heap. Okay, before moving on to the implementation, we must know there are, two heaps. Okay, one is the main heap and the other is the max heap. Okay, max heap. Now let me tell you the difference. Okay, so both min heap and max heap are complete binary tree. Okay, now we must see how the elements are stored. Okay, so let's suppose I have 5 elements. Okay, uh, so the heap should look like this, right? It is a complete binary tree, so it should look like this, uh, if the heap is having 5 elements. Okay, let's suppose I pass 5 elements into the min heap and the max heap. Okay, so the 5 elements are, let's say, 5, 7, 9, uh, minus 3 and 11. Okay, so these are the 5 elements. So if, you know, if I insert these elements into min heap and if I insert these elements into max heap, they'll be stored differently. So according to min heap, what happens is, the smallest element is at the top. Okay, and the childs of this the childs will have greater value than the parent. Okay, so this node is the root node is the parent for these two nodes, right? This node and this node. So the value of these two nodes will be greater than the root node. Okay, and likewise, so this node value has has less value than these two. Okay, so this is the way in which the elements are stored in the min heap. Okay, and in the max heap the topmost element will be the maximum, okay, and the childs of a node are always having a value smaller than the parent node, okay. So let's suppose I insert these elements into the min heap, so the elements will be stored like this, okay. So minimum element will be at the top, so minus 3 is stored here, okay. Now uh, the elements that are stored below it will be greater than that particular value, but they should be smaller than the nodes below it, okay. So we must choose minimum to maximum, right? Minimum to maximum. So the order downwards is min to max in the case of min heap, okay, and the order downwards in the max heap is max to min, okay. So let's just put the elements into it. So the elements greater than minus 3 are 5 and 7, which are less than 9 and 11, okay. So 5 and 7, okay, and 9 and 11 are greater, so 9 and 11. The elements that are stored here doesn't matter if their, if their children's are below, are greater than them, okay. So let's suppose I insert 7 here and 5 here, 9 and 11 here, even then this will be a min heap, okay, because every node, no, the child of every node has a greater value than the node itself. So root node has minus 3 as the value, but the childs of the root node has greater value than the value of the root node itself. So 7 and 5, right, both are greater than minus 3. So the childs of 7 node 7, this node, okay, node having the value 7 has greater values, okay. So one is having value 9 and another one is having value 11, which is greater than 7 itself, right. So this is how the elements are stored in a min heap, okay. This left to right order doesn't matter until it follows the order from the top to bottom, okay, like min to max. So upward, the top element will be always the minimum element, okay, in the number of elements that we are given. So now in max heap the maximum element will be at the top and the children's below it will have a smaller value than the node itself. So 11 is stored at the top because it is the maximum, okay. Now the children's below it will have a smaller value, okay. So the 7 and 9 are stored in the second level, and in the third level minus 3 and 5, okay. I already told you that the left to right order doesn't matter. So, minus 3 could be stored here as well, okay, and 5 here, okay, and even 9 and 7 can be, reversed because even if 9 comes here, then the values, the children's are still lesser than the value 9, okay. Max to min is the order in which we are going to store the elements. So this was all about max and min heap. This was all about the differences. So a structure of max heap, min heap stores the element this way and max heap stores the element this way, okay. So now let's just talk about the implementation, okay, and then we'll code the implementation, okay. So let's zoom it, okay. Let's yeah. So now when we talk about the implementation, okay, before the implementation we'll talk about the advantages, okay. Advantages of heap or binary heap, okay. Advantages of binary heap. So the advantages are, the first advantage is that a binary heap helps in heap sort, okay. Heap sort, a heap sort is a sorting algorithm which takes big of 1 space complexity, okay, and big O of n log n time complexity, okay. If you know about the time and space complexity, then that's fine, but if you don't bother, okay. Heap sort is just a sorting algorithm which is used to sort an elements in the array, okay. That's it, okay. It is a sorting algorithm, so you must remember this as a sorting algorithm, okay. Just like quick sort, merge sort, and insertion sort, bubble sort, just similar to them, but it has slightly lower time complexity. Although the sort function that we use in the algorithm, in the standard template library, we have a library called algorithm, and we use sort function here. It also gives us the same time complexity, which is n log n, okay. But knowing the heap sort is pretty useful sometimes, okay. So the second advantage is uh, in implementation of priority queue data structure. Okay, implementation of priority queues data structure, priority queues. Okay, so yeah, it is used in the implementation of priority queue. Now let us quickly jump in the implementation part of the binary heap. Okay, so let's just talk about the implementation. Okay, how this uh, binary heap is implementation of binary heap. Okay, so first thing in the implementation. Okay, so what we'll do, a binary heap, we have to implement it, we are implementing this binary heap as a class. Okay, so let's say class, and let's say we first try to implement min heap. Okay, or the min heap and max heap will both have the same, similar implementation, but the functions will be different, right? So we'll create different functions for both of them, but the implementation, let's say we call it class heap. Okay, inside this we give the access modifier as public. Will have three things. Okay, we'll have three attributes. So first one is the size of the binary heap. Okay, the elements that are stored in it. Okay, second thing will be the capacity. Capacity will be different from size. Okay, capacity is the elements that it can store. Okay, and the third thing, let's say we take an array. Okay, we don't take an array, rather what we'll do, we'll take a pointer here, integer pointer, which will point to an array. Okay, yeah. So now we'll create a constructor here. Okay, so constructor function. Okay, constructor function, or you can simply call it constructor. Okay, doesn't matter. Now inside the, so I should, okay, so min heap, sorry, uh, it should be heap, right? Heap, then let's say we pass capacity. Okay, so that we can assign capacity. So capacity becomes C. Size we will assign 0 to it, because size increases as we insert the element. Okay, and to insert the elements we'll create another function. Size is 0 and ARR is equals to new int of capacity C. Okay, so this will be the constructor. Now uh, to move to check the left node, right node, they will also have some index in the array, right? So int left, because it will return us the index of the left element. Okay, so return 2 into I plus 1. Okay, where I will be the index of the node that we are currently at. Okay, int right. Okay, int I, for right, the index of the right node will be 2 into I plus 2. Okay, and finally the parent. Okay, the parent will have an index. Okay, int parent, let's say the index we are at is I, so the parent of I will be return I minus 1 by 2. It should be floor, but we don't need floor here. Okay, because the integer division is there, right? So let's just talk about this. Okay, let's just quickly talk about this structure. Okay, okay, yeah, we are fine. So let's say we have a heap. Okay, let's say we have a heap here. So let's say this is a heap. Okay, okay, let's say this is a heap having 5 elements. Okay, let's say that this heap is a min heap. Okay, when we implement it. Okay, so what we'll do, let's say, so the root node here in this heap. Okay, root node will always have an index I equals to 0. Okay, I already told you that it is implemented as an array. Let's say the array looks like this. Okay, so it has 1 2 3 4 and 5. Okay, 5 spaces, 0 1 2 3 4. Okay, now let's say the heap is, we pass 5 elements to it: 2, 8, minus 5, 6 and 9. Okay, so in a min heap the elements will be stored something like this. Okay, minus 5, the minimum element will be at the top because it is a min heap, right? Then slightly greater elements, so 2 and 6 are the slightly greater elements, and then the largest elements at the bottommost position, so 8 and 9. Okay, so this is how the min heap looks like. Okay, now this index will have, the root node will have an index 0 always. Okay, now to know the index of this left node and to know the index of this right node, which is the right child, okay, we use these functions. Okay, so for left, okay, we'll pass the index of the root node here because we are currently at root node, right? So let's say the index is 0. Okay, if we pass 0 in this function, 0 I equals to 0. Okay, we get what, 2 into 0 plus 1 in return, which is 1. 2 into 0 is 0 obviously. Okay, and 1 is remaining, so we get 1. So the index of the left part will be 1. Okay, this is what this function says. If we are at particular index, to get the index of the left part of it or left node, we are going to use this left function. To get the index of the right node, we'll use the right function. So if we pass I equals to 0 here, okay, we get 2 into 0 plus 2, which is 2. So the index of this part will be 2. Okay, so how they're stored in the array? So the first element will be I equals to 0 equals to minus 5, right? So minus 5 will be stored here in the array at the 0th index. At the first index I equals to 1, 2 is stored. At the second index 6 is stored. Okay, now again, uh, this is 1. Now we have to find the index for uh, the childs of the left node, right? Because it has only the child. For the right node we don't have to find the left and right because it is not having any of the child. If it was having a left child, then we would find the left from the left function, the index of the left child. But as uh, it is not having any of the child, we won't find any indexes of left and right for this particular node. So we'll find the indexes for this particular node. Okay, so if we pass I equals to 1 to the left, okay, I equals to 1, it gives 2 into 1 plus 1, okay, which is 3. 2 into 1 gives 2 and 2 plus 1 is 3. So the index of the left part will be I equals to 3. Now for the right, if we pass I equals to 1, it gives us 2 into I plus 2, right? So 2 into 1 plus 2, it gives us 2 into 1 is 2 and 2 plus 2 is 4. So it gives us 4. So the index of this element will be 4. So how they're stored in the array is, at the third index 8 is stored, so 8 is stored here. At the fourth index 9 is stored, so 9 is stored here. So this is how the elements are of the of this min heap are stored in the array. Okay, so this is ARR. Okay, this is the ARR array. These elements can, can have the value replaced. Okay, 6 can come here, 2 can come here, and 9 can come here, 8 can come here, but the order will be that the minimum is at the top and the maximum are at the bottom. Okay, so this is what the order is. So now let's get back to the Visual Studio Code and let's try to implement a heap. Okay, in the max heap also the indexing will be the same way, but the element are stored in the different manner. Okay, so when we push these elements, let's just look at this as well. Okay, so when we push these elements into a max heap, okay, the elements are stored this way. Okay, so it has 5 nodes, right? And we need to make sure that it is a complete binary tree. Now the elements are stored in this way. So the maximum will be at the top. Okay, because this is a max heap. Okay, max heap has max to min. Okay, the downward order. Okay, so maximum will be at the top and minimum will be at the bottom. So what is the maximum? Maximum is 9. Okay, out of these elements, right? So maximum is 9, then 8 and 6 are the second maximum, 8 and 6. Okay, either you write this way or you write 6 and 8, doesn't matter. Okay, because we only need to make sure that the elements below a node should have greater element than their parent elements. Each node, the elements that each node is having, the value that each node is having should be minimum than the parent of it. So 6 is less than 9 and 8 is also less than 9. Okay, now we are left with only two elements, 2 and minus 5. Okay, so minus 5 is having less than 6, the value less than 6, and 2 is also having value less than 6. So this is the correct order. Okay, so this is an example of max heap. Okay, max heap. Now the indexing will be same way. Okay, so this is I equals to 0, this is I equals to 1, this is I equals to 2, this is I equals to 3, and this is I equals to 4. So the array, okay, the array for this particular max heap looks something like this. Okay, so let me draw the array. So let's say this is the array 1, 2, 3, and 4 and 5. So let's give them indexing as well. Okay, yeah, so 0, 1, 2, 3, and 4. Okay, so 9 will be stored at the first position, then 6 at the I equals to 1 index, at 2 index 8 is stored. Okay, at 3 index 2 is stored, and at 4th index minus 5 is stored. Okay, now if we try to print it, we are going to get this order. We can get 8 and 6 replaced and 2 and minus 5 replaced because they are at the same level and they have the value less than their parent. Okay, now let's try to implement this in the Visual Studio Code. Okay, so yeah, let's create heap dot okay, so let's write the boilerplate code now. Okay, IO stream. Okay, using namespace standard. Okay, now we create a class. Okay, class, let's call it heap. Okay, now within this class, let's say we give access modifier. The access modifier is public, so we give three variables to it: in capacity, okay, and then in integer pointer, right? Now to create the heap, we'll create the constructor. Okay, constructor function. Okay, so it should have the same name as the class, right? In C, we are going to pass C as the parameter. So capacity is going to be C, size is going to be 0, and ARR is going to have new integer array of size C. Okay, now to get the left, okay, to get the left index of a particular node, we will return 2 into I plus 1, right? 2 into I plus 1. Okay, and to get the right index, we'll get, what we'll do, int I, we will return 2 into I plus 2. Okay, and finally we are going to get the parent, we are going to use int parent. Okay, return I minus 1 by 2. Okay, so this is how we are going to implement the heap. Let's create an object of this. Okay, static allocation I'm going to use here. Okay, static allocation, object creation, whatever you can say. So heap m, okay, and let's give it a size 5. Okay, now let's try to insert these 5 elements. Okay, so the elements that we already inserted, so minus 5, 2, 6, 8, and 9. Okay, so let's get back. M dot, okay, now we will have to know how do we insert these elements. Okay, I have created a heap already. Let's try to print the elements of the heap. Okay, for int I equals to 0, I is less than capacity I plus plus. Okay, so the capacity should be of the heap, so m dot capacity, right? Cout m dot arr of I, it would give us either 0 or some garbage value. Let's see. Yeah, so it gives garbage value for all the elements. Okay, because we haven't inserted elements right now. So now just let's look at the implementation of the insert function. How do we insert the elements into it? Okay, we just inserted the elements as per the definition, right? Now let's look at the implementation function. Okay, so let's look at the implementation part now. Let's should we add a new page or should we implement it here? So let's add a new page. Okay, let's just oh, I'm sorry. uh, yeah, let's move it a little bit. So let's just write the implementation. Okay, so implementation of insert function. Okay, insert function. So how do we insert an element in the min heap? Okay, so let's suppose by giving this particular statement, okay, this min heap m and 5, what we'll get, we will get a min heap which is an array of size 5. Okay, so there will be 5 portions in it. Okay, each having index this way, and there are some garbage value in each one of them. Okay, till now. Okay, it has capacity as 5 and the size as 0, because this is what we defined in the constructor, right? We'll pass the capacity, and capacity becomes the value that we have passed in the parameter of the constructor, right? Sorry, of the constructor. So now let's say for inserting, this will be the function. Okay, void insert. Okay, so we are going to pass some particular value to it, right? So let's say the value is int x. Okay, we are going to insert this value into the heap. Okay, so now what are the conditions? Okay, what are the different conditions to check? Okay, so first condition will be that the heap is completely filled. Okay, so all the elements are filled completely. Okay, so in that case, what will be size equals to capacity, right? This will be the condition of size equals to capacity. Okay, so if size is equals to capacity, then in that case we don't have to do anything, we have to just return. Okay, because we cannot fill any more, we cannot insert any more elements into it, right? The second condition that we have to check. Okay, so these are conditions. Okay, conditions that we have to check. Okay, so the first condition is this. Second condition is that the size is equals to 0. Sorry, uh, am I correct? Yeah, so the second condition, or we can just ignore this condition. Okay, because if size is 0, we have to insert, right? We don't have to fetch the elements. So what we'll do now, if the size is equal to capacity, then return. Otherwise what we'll do, we'll increase the size. Okay, we'll increase the size, and then we will put the element at the last index. Okay, so arr size minus 1 equals to x. Okay, now what we'll do, to move it upside in the, to move it either up or down, basically we will move it upside, because it is already positioned at the last position, right? So what we'll do, for loop we can use here, for int I equals to size minus 1. Okay, I does not equals to 0, I does not equals to the index of the root node, and arr of parent of I is having a value greater than arr of I. This function I'm implementing for the insert function in the min heap. Okay, so wait a minute, there will be semicolon, right? Because we are not assigning the expression here. Okay, we'll assign the expression within the for loop. Okay, so what we'll do, we'll swap arr of I with arr of uh, parent of I. Okay, parent of I. Okay, and then what we'll do, I equals to parent of I. we could have written this condition over after this semicolon, but to make it more easier, I've written this explanation here. So the function will look something like this. Okay, so the function, let's move on to the function. This was the function, right? Let's erase all of this so that we get the space. Only one condition that we have to take care of is size, when size is equals to capacity, right? Okay, so this much is fine. Okay, so the function will be something like this. Okay, so if size is equal to the capacity, if size is equal to the capacity, so if size is equal to capacity, okay, then in that case we have to return simply. Okay, we don't have to insert any element because already the heap is completely filled, right? But if it is not, then what we have to do, we can use a for loop here. For int I equals to sorry, not the for loop actually. What we'll do, we'll increment the size of the heap. Okay, and we'll at the last index, we will insert an element 5. If let's say we'll insert the element x, not 5. Okay, so 5 is the capacity, right? X will insert the element x. Okay, now we can use for loop here. For int I equals to size -1. Okay, I does not equals to 0, so until I reaches the index of the root node and arr of parent of I. Okay, so we'll try run this code. Okay, don't worry, we'll try run this code. Okay, how it works and all. So if arr of I, arr of parent of I, okay, is greater than arr of I, okay, then what we'll do, we'll swap arr of I with arr of parent of I, and I becomes parent of I. Okay, now this is the complete function. Okay, and this function is for the min heap. Okay, for the insert function in min heap. Okay, so let me write this. So inserting element in min heap. Okay, min heap. Okay, now let's just see how we insert these elements. Okay, let's move to the previous page. So we inserted 2 8 minus 5 6 9, right? So 2 8 minus 5 6 9. Okay, 2 8 minus 5 6 9. Okay, let's just say we try to insert these elements into a min heap. Okay, so there are five you know 5 elements, so we will create a complete binary tree. Okay, so this will be this is how the complete binary tree looks like. Okay, and the array looks like this. Okay, the array looks like this. So 1 2 3 and 4 and 5. Okay, so 0 1 2 3 and 4. The last index is less than the size, right? One less than the size. So now uh, for the first case, when we try to insert 2, the size is 0, right? So let me write here. Okay, so size is 0 and capacity is 5 because because we have assigned the capacity at the start, right? And then we are trying to insert 5 elements. So size is 0, capacity is 5. Okay, now the size is not equal to capacity, right? So we move to the next position, we move to the next expression. So size plus plus, so size becomes 1, and then arr of size minus 1 equals to x. So arr, this is the array, right? This is the arr array. So arr of size minus 1, that is arr of 1 minus 1, which is 0. Arr of 0 is equals to x. So 2 we are trying to insert, right? We will insert, when we write insert 2 here for the first element, right? So arr of size minus 1, that is 1 minus 1, that is 0. Arr of 0 equals to the element itself. So 2 is inserted. Okay, and now what we do, for I equals to size minus 1, so I is equal to size minus 1 is 0, and I does not equals to 0, which is the condition false. Okay, the condition is false, so I is equals to 0, right? So this complete for loop won't run. Okay, so this won't run, and hence only the element is inserted. Okay, only 2 is inserted. Now for the second case, if you write insert 8, So size is already 1, right? Size is 1, and the capacity is also, capacity is 5. Okay, capacity is 5. Okay, so what happens is that, okay, let's move from here to here. Okay, so the, size is not equals to capacity yet. Okay, 1 is not equals to 5, so size is incremented again. Okay, this is skipped, this particular expression, this particular statement is skipped. Size is increased, so size becomes 2. Size becomes 2, and ARR of size minus 1, that is ARR of 2 minus 1, ARR of 1 becomes x. So x is nothing but 8, the element we are trying to insert, right? So ARR of 1 becomes 8. Okay, ARR of 1 becomes 8. So we have to, just write these elements over here also. Okay, so I0, this one is I equals to 0, this one is I equals to 1, this one is I equals to 2. You can use the functions, okay, to get the indexes. This one is I equals to 3, and this one is I equals to 4. Okay, now at 0 we have inserted 2. Okay, yeah, till now. So now insert 8. Okay, after inserting 8, we have inserted ARR of size minus 1 equals to x. Size minus 1 is 2, because size has become 2 now, right, after incrementing. So ARR of 2 minus 1, that is ARR of 1 becomes 8. Okay, now we are trying to run the for loop. Okay, for I equals to 2. Okay, sorry, I equals to size minus 1, not 2 actually. Size was 2, so I minus 1 will be 1. Okay, I does not equals to 0. Yeah, this condition satisfies. And ARR of I, ARR of parent of I. Okay, this last condition, ARR of parent of I. So parent of 1 is 0, right? Parent of 1 is 0. So ARR of 0 is greater than ARR of 1. Okay, greater than the ARR of 1. Okay, the value at ARR. So this is not the case, because 2 is not greater than 8, right? So this swap function do not take these statement within the for loop won't execute it again, won't be executed. Okay, so yeah, these statements won't be executed again. Okay, again they are skipped. Okay, so now the size has become 2, right? So if we try to insert another element, let's say we try to insert minus 5 now. So what happens? Okay, what happens is that, let's try to move it a little bit. So size is 2 already, right? Size is 2, and capacity is equals to 5. Okay, now still the size is not equals to capacity. So what happens is that size is incremented, so size now becomes 3. Okay, size now becomes 3, and ARR of size minus 1, which is 3 minus size minus 1, okay, is equals to ARR of 2, right? Because size is 3 and size minus 1 is 2. So ARR of 2 becomes minus 5, because we are trying to insert minus 5, right? So ARR of 2 becomes minus 5. Now for loop runs. So I equals to size minus 1, from size minus 1, that is 2. Okay, I does not equals to 0, and okay, ARR of parent of I. So I is 2, parent of I is 0, right? Index 2 also has parent having index 0. So ARR of 0 is greater than ARR of I itself. So ARR of 2. Is this the case? Okay, let's check. So ARR of 0 is 2, right? ARR of we assigned ARR of 2 as minus 5. So let's put minus 5 here. Okay. Now ARR of 2 is minus 5. 2 is whether 2 is greater than minus 5. Yeah. So 2 is greater than minus 5. So in this case, the statement within the for loop runs. So what are the statement? Is that we have to swap the elements at these two indexes. Okay, 0 and 2. Okay. So what happens is that, let's try to erase it. Okay. So 2 goes at the second index and minus 5 comes at the first index. Okay, so minus 5 comes here and 2 goes at the second index. Okay, now I becomes what? I becomes parent of I, which is 0 only. Okay, now for the second case, when we check, I does not equals to 0, it says, but I has become 0. So for loop is not executed twice. Okay, so yeah, this was the thing. Okay, now for the fourth case, so size is already 3 now. Okay, and if we try to insert 6 now, okay, because fourth element is 6, right? Insert 6. Okay, this one. Okay, now if we try to insert 6, size is not equals to capacity. So first condition, size is 3 and capacity is 5, and size is not equals to capacity. So first statement of this function, this insert function, this first statement won't be executed, right? This statement. Okay, now we move to second statement directly. So size is increased and ARR of size minus 1 becomes x. So size is increased, size becomes 4, capacity is 5 itself. Okay, no change in the capacity, and ARR of size minus 1, 4 minus 1, which is 3, becomes what? 6, because we were trying to insert 6, right? Yeah, ARR of 3 becomes 6, so let's insert 6 here. Okay, so 6 is inserted. Let's put the elements here as well. Okay, so let's try to erase this. Okay, so 2 is going to be erased now, because after replacement minus 5 is the topmost element, right? Minus 5, then 8 at index 1, at index 2 2 is there, at index 3 6 is there. Okay, now what happens is that oh sorry, yeah, so uh, now for loop runs. Okay, we have assigned 3 equals to, for I equals to size minus 1, 4 minus 1 is 3. Okay, and I does not equal to 0, so 3 is not equal to 0, right? And ARR of parent of I, ARR of parent of I is 1, so ARR of 1 is greater than ARR of I itself, so I is 3, right? 3 for the first case, so I is 3. Okay, let's check whether this condition is true. If the condition is true, then the statement within the for loop will be executed. So ARR of 1 is 8 and 8 is greater than 6, right? So again the swap occurs. Okay, so the swapping occurs between element at index 1 and element at index 3. Okay, so 6 comes here and 8 goes at the index 3. Okay, so now what happens is uh, 6 comes here and 8 goes to the index 3. Okay, and now I becomes parent of I. Okay, so I becomes parent of 3, so I becomes 1 for the second case. Okay, for the second case I becomes 1. Okay, now we again check whether I does not equal to 0. Yeah, so this condition satisfies, but ARR of parent of I, that is 0, is it greater than ARR of I itself? So I is 1 here. Okay, let's check. So parent is minus 5, whether minus 5 is greater than 6? No. So the condition within the for loop won't be executed. Okay, and the for loop is terminated. Okay, now for the last case, when we try to insert the last element, which is 9. Okay, so we are trying to insert last element, so insert 9. Okay, so when we try to insert 9, what happens is that yeah, so size is 4, which is not equals to capacity, right? So again the size is incremented, size becomes 5, capacity becomes 5. Okay, and now what we'll do, we'll assign ARR of size minus 1, that is uh, this is going to be 4, right? ARR of size minus size is 5, so 5 minus 1 is 4, so ARR of 4 becomes the element. Okay, the value of the element, so 9. Okay, so let's insert 9. Okay, and here also ARR of 4 becomes 9. Okay, now what we are going to do is that we are going to check the for loop. Okay, for I equals to size minus 1, so 4, I equals to 4, I does not equals to 0, this condition satisfies, and the other condition should satisfy as well along with this, right? So the other condition is ARR of parent of I, parent of 4, parent of index 4 is index 1, right? So whether ARR of 1 is greater than ARR of 4, let's see. So ARR of 1 is 8, whether 8 is greater than 9? No. So this condition is false, hence the statement within the for loop won't be executed. Okay, they won't be executed, and we get uh, this as the final order of the min heap. Okay, so this is the final order, and this is the state, this is how the elements are stored in the min heap. Okay, so minus 5, 8, 2, 6, 9. Okay, let's just try to print the order and let's see whether we get the correct order or not. Okay, so the correct order is minus 5, 6, 2, 8 and 9. Okay, when we try to insert 2, 8, the order should be same as well. Okay, because in min heap what happens is these two can be replaced, right? Because we have to only check the order from top to bottom, right? So 2, 8 minus 5, 6, 9. Okay, we'll insert in the same order. Okay, so the output should be this. let me write here. So this is going to be the output. Okay, so this is the output and this is the input, right? This is the input. Okay, let's just implement this insert function. Okay, so to implement the insert function, what we're going to do, this is a void function, right? Insert okay, so int x, this element we are going to insert, right? So if size is equal to capacity, okay, then what we have to do is simply return. Okay, otherwise we have to increment the size. Okay, then we have to assign arr of size minus 1 equals to, okay, equals to x. Okay, now for loop we have to run for int I equals to size minus 1, I does not equals to 0, and arr of parent of I is greater than arr of I itself. Okay, then in that case we have to swap arr of I and arr of parent of I. Okay, parent of I. Otherwise sorry, and I equals to parent of I becomes parent of I, right? So this is what it becomes. Okay, now let's just try to pass the element in this order. Okay, and let's just try to print it. So this is for the printing, right? This for loop. Now try to insert it in the same order. Okay, so the order is let's just write the order of insertion. Okay, insertion is going to be something like this. Okay, so firstly minus 2 8 minus 5 6 and 9. Okay, so let's get back. 2, then we are going to insert 8. Okay, 8, then minus 5, then 6 and then 9. Okay, so let's just insert. Okay, m dot insert 2. Okay, let's just copy this. Then we are going to insert 8, then we are going to insert minus 5, then we are going to insert 6, and then we are going to insert 9 at the last. Okay, and let's see what is the output of the array. Okay, so there shouldn't be any problem. I think whether there is any problem or not. No, there is no problem, I think. Okay, I forgot to put the semicolon here. So now it's fine. Okay, so what we should get, minus 5 6 2 8 9. Okay, let's see minus 5 6 2 8 9. So this is the correct order, right? This is the order that we obtained here, right? So this is how the insertion in a binary heap takes place. In the next lecture we are going to talk about other functions that are used in the implementation of binary heaps. Till then, goodbye.